Greetings, algebra students. In this lesson, we're going to be looking at solving exponential and logarithmic equations. And the first thing we're going to start with is solving exponential equations. And there's really two situations that we're going to be looking at in solving exponential equations. So we're just going to do these situations kind of by examples. So what we're going to say is in our first example, where we have a variable in the exponent in only one location. Here I have 4 to the x is equal to 11. Don't confuse 4 to the x with 4x. An exponent is different than multiplication. Please make sure you're being careful and looking closely at the problems. Okay. So to solve this equation for x, we need to cancel out that exponent base of 4. Now, you can't divide both sides by 4 to cancel this because the 4 is not being multiplied to the x. The x is an exponent on the number 4. If you recall from the previous sections, when we talked about logarithms, we talked about how logarithm base b will cancel exponent base b. So I need to use a logarithm here to cancel this exponent base of 4. And the logarithm that I need to use in this case needs to match my exponent base. So I'm going to do log base 4 of both sides. Okay. Now we remember that log base 4 cancels exponent base 4. So we're left with just x is equal to log base 4 of 11. And this is something that we can evaluate on our calculator. So if we pull up our calculator and we go to the math button and we scroll down, to where it says log base, and we select that, we can type in the 4 for the base of the logarithm and 11 in the argument, and that gives me approximately 1.730. And whenever we're dealing with these solving logarithmic or exponential equations, if you round to 3 decimal places and when you're getting like an irrational number answer like that, that will be fine. Let's do another that's a little bit more complicated. Okay. So here we have a little bit more going on. We notice that we still have the x in just one exponent, which is good, but we have some other stuff going on before we can get to canceling the exponent base. Remember, when solving, we want to perform the order of operations kind of in reverse because we're undoing things. So the first thing we'd want to do is add 6 to both sides. Next thing we'd want to do is we need to undo that multiplication. So we need to divide both sides by 2. And now we're at a place where we can try to cancel the 3. So the 3 is an exponent base. And what operation do we know is going to cancel an exponent base? A logarithm. Which logarithm do we need? The logarithm that matches the exponent base. So I need to do log base 3 to both sides. So I know log base 3 cancels exponent base 3. So I'm left with x plus 5 is equal to log base 3 of 8. And then my last step here, oops, I've been writing those in black. Would be to get rid of the plus 5. So I'll subtract that from both sides. Now I notice that log base 3 of 8 and 5 are not like terms, so I can't subtract them directly. So I'm just going to write it at the end. And then I'm going to go to my calculator to get my decimal approximation. So I'll go back to the math menu, choose the log base command, log base 3 of 8, and then outside the parenthesis, I'll do the minus 5. So that gives me negative 3.107. Okay. So that's the first type of exponential solving problem we'll have to deal with, is when you have the exponent just in one location. The second situation is where we have exponents in more than one location. So let's say, for example, we have 4 to the x is equal to 1/2 to the x minus 3. So my goal in a situation like this, where we have variables and exponents in two different locations, is I'm going to try to rewrite the bases of these exponentials so that they have a common base. Okay. So the base that I can use that's going to be common to both 4 and 1/2, I know 4 is 2 squared, and I know 1/2 is 2 to the negative 1. Because remember the exponent rule, a to the negative n is 1 over a to the n. So I'm going to use that to rewrite this as 2 squared to the 2x equals 2 to the negative 1 to the x minus 1. Now remember, we have a property of exponents that deals with when I have an exponent of an exponent like this. So a to the n to the m is a to the n times m. So 2 squared to the x becomes 2 to the 2x. And 2 to the negative 1 to the x minus 3 becomes 2 to the negative x plus 3. Now that the bases of my exponentials are the same, notice now that they're both 2. Now it's time to cancel the exponent base. To do that, we're going to use a logarithm. Which logarithm should I use? Well, it needs to match my exponent base. So I would do log base 2. Now remember that log base 2 cancels exponent base 2. And we're left with 2x is equal to negative x plus 3. And from here, we just add x to both sides. and then divide by 3 to get x is equal to 1. Okay. So let's do that one more time. So again, I notice that this is the situation where I have variables in more than one exponent. So my first order of business here is to look at the bases of these two exponentials and figure out a way to rewrite them so that they have the same exponent base. So I notice that 100 is 10 squared, and 1,000 is 10 to the third. So there's an easy way for me to rewrite these so that they have the same exponent base. So I have 10 squared to the 7x plus 1 equals 10 to the third to the 3x minus 2. Now remember, when I have an exponent of an exponent, like we do in this situation, that we multiply them. So 2 times 7 is 14x, and then 2 times 1 is 2. And similar on the other side, so 3 times 3x is 9x, and 3 times negative 2 is negative 6. So now that I have these exponentials rewritten so that they have the same base, I can now cancel the base with a logarithm. So the logarithm I need to use is the one that matches this exponent base. So I need log base 10 in this case. But remember, we don't write log base 10 with a 10 down there. This was one of them that we have an abbreviation for. So log base 10 was called the common logarithm, and the way we write it is just log with no base there. Remember, if you see a log without the base, what we mean is log base 10. So log base 10 cancels exponent base 10. We're left with 14x plus 2 equals 9x minus 6. And then to solve from here is pretty easy. We'll subtract 2 from both sides and subtract 9x from both sides. That leaves me with 5x on the left-hand side and negative 8 on the right-hand side. And if I divide by 5, then I have just x is equal to negative 8/5. Would we feel okay here? I hope so. Next up, we're going to talk about solving logarithmic equations. Okay, and there's going to be 3 types of logarithmic equations that we're going to be interested in solving. And again, just like we did for the exponentials, we'll talk about each of the different types with examples and how to kind of distinguish between the 2 or the 3 different situations. Okay. So the first situation is where you have exactly 2 logarithms that are equal to one another. Okay. So in this case, let's say we have log base 5 equals 4x minus 7. I'm sorry, log base 5 of 4x minus 7 equals log base 5 of x plus 5. The first thing we'd want to do is observe that we just have two objects. We have log base 5 of some stuff equals log base 5 of some other stuff. So this is the easiest situation. Here I just want to cancel the logarithms, and since they're the same logarithm and there's just the one logarithm on each side, this is pretty easy to do. So what I'm going to recall is that an exponent base b cancels logarithm base b. So what I need is to do an exponent base to both sides. The exponent base in this problem that I need should match my logarithm base. So that's going to be exponent base 5. And now I'm going to write the 5 really exaggeratedly, comically big, just to reemphasize that this exponent base 5 is not multiplication. I'm not doing 5 times log base 5 of 4x minus 7. I'm doing 5 to the power log base 5 of 4x minus 7. So I know exponent base cancels the log base. And where we're left at is just that 4x minus 7 is equal to x plus 5. And from here, things are pretty easy. I'll start by subtracting x from both sides and adding 7 to both sides, giving me 3x equals 12. And when I divide both sides by 3, I get 4. However, I'm not done. So for all logarithmic equations, I still need to check. So what does checking look like? It means that when I plug that 4 back into the original equation, I get the same answer on both sides of my equation. So I'm just going to do this with my calculator. So I'm going to get log base 5 of 4 times 4 minus 7. So that's me just plugging 4 in for x into the left-hand side of my original equation. You got to start at the very beginning when you do your checks. And it gives me this number. I need to now make sure I get the same number from the right-hand side. So I'm going to do log base 5 of 4 plus 5. And I get exactly the same number. So what that means is that this solution works. And I'm just going to box it up and put a check mark next to it to indicate that I've checked this and this solution does indeed work. If that solution had failed, I would just put an X through it and write no solution. When the solution fails a check like that, what it means is it's an extraneous solution. Let's look at the second situation. So the second situation is I have one logarithm and then some non-logarithm parts. So my one logarithm is log base 4 of 5x minus 1. And my non-logarithm part in this case is the 3. So the first thing I want to do is to isolate my logarithm. That's already done, right? The logarithm is all by itself on that left-hand side. So now I'm ready to cancel that logarithm. So to cancel log base 4, I need to use exponent base 4 to both sides. So I'll write my big 4 to both sides. And then in the exponent, I'll write log base 4 of 5x minus 1, and then a 3. And now I know log base 4 cancels exponent, or exponent base 4 cancels log base 4. leaving me with 5x minus 1 equals 4 to the third. Now, this is the place where if you're struggling with exponent base versus multiplication, it's really going to jump up and bite you, because it's a common mistake. I see students writing 12 here. I see them doing 4 times 3. We're not multiplying here. We're using an exponent. So I want 4 exponent 3, which is 64. Next, I'll add 1 to both sides. That gives me 5x equals 65. And when I divide both sides by 5, I get 13. And now I just need to check this by plugging that back in for the x in the original equation. And since I have only variables on one side of this equation, I just need to see if I get 3 as my answer from the left-hand side. So math log base 4 of 5 times 13 minus 1. And I do indeed get 3, so I know this answer is correct. Put a check mark next to it and box it up. Let's do one more, kind of in that type. That's a little trickier, maybe. Okay, so let's say we have 2 times the natural log of 2x plus 5 plus 6 equals 18. So again, the first thing I want to do is to isolate the logarithm. So I got to get rid of the plus 6 first. And then I have to get rid of the times 2 after that. And now it's ready to get rid of the natural log. So I remember that an exponent base is going to cancel out a logarithm. The problem is there's no base written next to this ln symbol. But if you recall back a few sections, this ln symbol was the natural log. This was one of those special logarithms that got an abbreviation. So remember, the base for the natural log is e. We don't ever write the e as the base. We write the symbol ln, but we understand the base for this logarithm to be that irrational number e that we talked about a couple days ago. So I'll write my big E, and then my exponent will be natural log of 2x plus 5 equals, and then my other exponent will be 6. So I know natural log E, or E, exponent base E is going to cancel the natural log. That's how I want to say it. Leaving me with 2x plus 5 equals e to the 6th. And e to the 6th is just something I'm going to type into my calculator, but I'm going to do that kind of all in one step at the end rather than making it a decimal right now. So we'll subtract 5 from both sides. Now those are not like terms, so I'll just write e to the 6th minus 5. And then we'll divide both sides by 2. And again, not like terms, so I'll just write that as e to the 6th minus 5 over 2. And that's what I'm going to type into my calculator. So when I have a fraction like this to type in my calculator, the way I like to do that is press the alpha button and the y equals. This opens up the fraction options. And the first fraction option allows me to write this as like an improper fraction. And this is really nice because I can type it in exactly the way it looks on my sheet of paper, and I don't have to worry about making sure my parentheses are right or whatever. So when I do that, I get 199.214. And again, we should check this, and we need to check this back at the original. But notice I only have x's on one side, so all I really need to do is plug that number in for x and see if I get 18. And I'm going to do this all in my calculator because there's kind of a slick way to do this. So 2 times natural log, 2 times, and then I want this number from before, so I can either scroll up and press enter, and it'll put it down in that spot, or I can press second and the negative sign to get this ANS, which is just shorthand for the previous answer. And then I'll do the plus 5, close my parenthesis, and do the plus 6, and see if I get 18. I do! So that tells me that this answer is correct. Okay. My last type of problem is one where I have two logarithms and a non-logarithm. So for example, here we have log of 2x plus log of x minus 5 equals 2. So I have one logarithm, log of 2x. I have a second logarithm, log of x minus 5. And then I have a non-logarithm, that's the 2. So my first order of business is to condense my two logarithms into a single logarithm. So if you remember from the previous lesson, that if I have the sum of two logarithms, I can rewrite that as a product inside the logarithm. And I'm just going to go ahead and distribute that 2x through. And now I'm going to cancel the logarithm. Since I have just a single logarithm on the left-hand side, it's now okay for me to cancel that exponent, or cancel that logarithm with an exponent base. Oh no, there's no base written next to this logarithm. Oh, what does that mean again? Oh, I remember. It means the common logarithm, its base is 10. Whenever I see log written and there's no number written next to it, no base, I understand the base for that logarithm to be 10. So I'll write my big 10 on both sides. And the exponent on the left-hand side is going to be log of 2x squared minus 10x. And on the right-hand side, it's going to be 2. So remember, exponent base 10 cancels log base 10. So I'm left with 2x squared minus 10x is equal to 10 squared, not 10 times 2. Again, have to be careful that you're using an exponent and you're not thinking about that as multiplication. Okay? So what I'm left with is a quadratic equation. To solve a quadratic equation, the first step would be to make it equal to 0. So I'll subtract the 100 over to the left side. And I notice here that, write that down, that each of the coefficients, 2, 10, and 100, are all even numbers. So if I divide both sides by 2, I can make this problem a little bit easier. So 2 divided by 2 is just 1. 10 divided by 2 is 5. And 100 divided by 2 is 50. And 0 divided by 2 is 0. What I'm left with then is still a quadratic equation. And to solve this quadratic equation, I can either factor or use the quadratic formula. Since the leading coefficient for this quadratic is equal to 1, I'm going to try to factor it first, because if I can factor it, it should be pretty easy. So what I'm looking for are, what the heck just happened? Excuse me there. Are two numbers that multiply to give me -50 and then add to give me -5. Oh, I see the two numbers. They are -10 and +5. Those multiply to give me -50 and add to give me -5. Since the leading coefficient for that quadratic is 1, I can go straight to my factored form. X minus 10 times x plus 5 is equal to 0. I'll then apply the zero product property to write this as two equations. X minus 10 is equal to 0, and x plus 5 is equal to 0. To solve the first equation, I'll add 10 to both sides. To solve the second equation, I'll subtract 5 from both sides, giving me solutions of x equals 10 and x equals -5. However, we're not done. We still have to check. So to check this, what I'm going to do is I'm going to go back to the very original, plug 10 in for x, and see if I get 2. I do! So 10 works. Now let's try -5. Oh no, we got an error. Why did we get an error here? Well, remember our definition for a logarithm, and I know this was a long time ago. Actually, let's summarize a few things real quick. So this worked. This one doesn't. We got that error. I want to go back and look at why we're getting the error, though. So recall our definition for logarithm said for y and b being positive numbers, log base b of y is equal to x if and only if b to the x is equal to y. So for a logarithm, the argument, the part inside the logarithm, has to be greater than 0. It must be positive. If I plug -2 in for x, or I'm sorry, if I plug -5 in for x, I get -10. If I plug -5 in for x, I get -10. I can't take the logarithm of a negative number. That's why we're getting an error. That's why that solution is mumbo jumbo, and we're left with really just one solution. So we really have to make sure we're checking, because there are times where you're going to get things like this where the solutions just don't work. Let's do one more example of this before we finish. So let's say we have log base 4 of x plus 12 equals log base 4 of x, which is equal to, oops, I meant plus here, which is equal to 3. So again, the first step that I want to do is I want to condense the left-hand side into a single logarithm. So I'll use the product property for logarithms to rewrite this as log base 4 of x times x plus 12 equals to 3. And then I usually like to just distribute inside my logarithm there. the next step would be to cancel the logarithm. So log base 4 will be canceled using exponent base 4. So I'll do my big 4 to both sides. And then my exponent is going to be log base 4 of x squared plus 12x equals 4 to the third. So log base 4 and exponent base 4 will cancel each other out, leaving me with x squared plus 12x equals, and then we did 4 to the third just a bit ago. I remember that was 64. And what I'm left with is a quadratic equation. To solve a quadratic equation, it has to first equal 0. So I'm going to subtract 64 to both sides. And now because the leading coefficient is 1, I'm going to try to factor this. You could still use the quadratic formula. That would be fine. To me, it seems like this is just going to be easier to factor. So I'm looking for two numbers that multiply to give me negative 64 and add to give me positive 12. So those two numbers are, I got them. Did you got them yet? Positive 16 and negative 4. So I can go immediately to x plus 16 times x minus 4 equal to 0. And then apply the zero product property. That lets me set each of those factors equal to 0. And when I solve, then I get negative 16 and positive 4. But I'm not done. I have to make sure I go back and check. So I'm going to plug negative 16 in here. And I can see already before I even try to get this into my calculator, I'm going to be getting an error. Because negative 16 plus 12 is negative 4. And I can't take the logarithm of a negative number. So already, I can see that negative 16 won't work. You can try it in your calculator if you feel like it. It's just going to give you an error, that same error that says non-real answer that we got before. However, if I look at 4, that'll give me positive 16 and positive 4. There's no problems there, so let's actually check that in our calculator to make sure. So we'll go back and grab that log base command. So I've log base 4 plus 12 plus log base 4 of 4. Press enter. And I do indeed get 3 as I was hoping for. So I do have just the one solution. Okay. Don't be confused now. We've seen a couple of examples on these third type of logarithm solving logarithms problem that one answer has worked and the other hasn't. It will not always be that case. Okay, it's possible that both answers work. It's possible that neither answer works. You don't know until you check. So don't just assume one's going to work and one won't. That will not always be the case. This wraps up the section on solving exponential and logarithmic equations. So we'll stop here. I've posted an assignment, worksheet 6 to PowerSchool, and you should do that after watching this video. Okay, bye-bye.